Hello and welcome to this lecture. So, we saw earlier that to understand how the span of two vectors behave, we need to know about linear independence and dependence, because when they are linearly independent, you go to one higher level of dimension. When they are linearly dependent, you fall back to the original one. Okay, so you can imagine when you look at span of more than two vectors also, the same idea is very crucial, and it is. Okay, so to understand the span of multiple vectors, V1 through Vk for instance, we have to know and extend the definition of linear independence to that situation. Okay, so here is the definition, and it plays a crucial role in understanding subspaces, spans, membership, solving linear equations, all of them. Okay, so here is the definition. K vectors V1 to Vk in Fn, right? When I don't mention anything, it is these vectors are in Fn because Fn is the vector space we are considering. And remember what F is. F could be real numbers R or complex numbers C. Okay, so these V1 to Vk are said to be linearly dependent if there exist scalars C1 to Ck such that C1 V1 plus so on till Ck Vk equals 0, with at least one of these scalars being non-zero. So, basically if there is a non-trivial linear combination of the vectors V1 to Vk giving you the 0 vector, then those vectors are linearly dependent. Okay. So, of course, they are linearly independent if no such thing is possible, right? The only way to get a linear combination of V1 to Vk to be 0 is the trivial combination with all the scalars being 0. That is a linearly independent situation. So, these two situations are very different in their nature, right? How the span works differs fundamentally depending on whether or not they are linearly dependent or independent. Okay. So, there is a special case here. These kind of special cases always occur. What if the vectors are all 0 and all that? I will not pay too much attention to it. Most of the time, if you carefully apply the definition, it will work out. In most cases, they are sort of trivial, but they can play a role in practice. You should understand what happens in these corner cases. Supposing one of the Vi is 0, okay, right? It's sort of ridiculous, but still, what if one of the Vi is 0? If one of the Vi is 0, then the set is linearly dependent, right? Because what you can do is, you can make the coefficient corresponding to that vector to be a non-zero scalar, make everything else as 0 scalar, so that linear combination will be 0. So, clearly, those vectors are linearly dependent. If any one of them is the 0 vector, then the linear combination is also can be made 0, a non-trivial linear combination can be made 0. So, the vectors are linearly dependent. Usually, we won't ask this question, but this can be important in practice. Okay. So, how do you determine whether a given set of k vectors are linearly dependent or independent? You have to use elimination again. You can imagine for two vectors we were using elimination, right? There was this very simple idea that if in one position you had a 1 and the corresponding position in the next vector you had a 0, those two have to be linearly independent. That same idea can be pushed to larger number of vectors, and elimination plays a key role in determining linear dependence or independence of a set of vectors. Okay. So, how do we do elimination for multiple vectors? Okay. So, let us start with coordinates. There are k vectors V1 to Vk. The coordinates are a11 to a1n, ak1 to akn. Okay, right? You can, so quite often people write this as a matrix, but we haven't come there yet. So, we will write it as coordinates, and you will see I am going to write it as a matrix quick enough, soon enough, and then work with it. Okay. So, first thing is we will assume pivots non-zero. Okay. So, we have been having these pivots play a central role in elimination, and they are very important. So, we will assume the pivots are first pivot is non-zero, meaning a11 is non-zero. I will come back and tell you what to do if the pivot ends up being 0. It's quite easy, the exchanges will work. So, we will say a11 is not 0 for now, and u1 I will assume I'll make u1 to be 1 by a1, a11 v1. So, I am making the first coordinate of v1 as 1. What will I do next is interesting. All the other vectors, right, vi, I equals 2 to k, right, v2, v3, v4 all the way to vk, I will eliminate with v1 and make their corresponding first coordinate 0. That I can do, no, because a11 is non-zero. So, I will do vi minus ai1 divided by a11 v1. This will make the first coordinate of all other vectors 0. I mean, I am manipulating, I am doing a linear combination to get new vectors with the first coordinate being 0. Okay. So, this is the crucial part here. So, u1 becomes just first coordinate 1 and all other ui's have first coordinate 0. Okay. So, notice how I am bringing in the linear dependence, linear independence easily established, right. So, so u1 is now linearly independent of all the other ui, right. Each of the other guys, you can't make a linear combination of all these guys go to 0 unless, so this u2 becomes etc. So, that linear independence is easy to establish. So, we get that. Okay, I hope you see that. Okay, so and you get some complicated stuff here. I mean, it's can be actual numbers when you put in. You'll get some actual numbers there, but in general, the expressions look a little ugly. So this is the first step in the elimination process. Okay, the crucial point here is that when I do this elimination, I have not changed the span. The span of V1 to Vk is the same as span of U1 to Uk. Proof is very simple. I'm not going to write this out for you. You can write any linear combination of V1 to Vk as a linear combination of U1 to Uk, and the other way around. Any linear combination of U1 to Uk can be written as a linear combination of V1 to Vk. So the span is not altered when you go through this elimination process. Okay, so this is very important. Okay, so the first step in the elimination, but we have k vectors, right? So when you had 2 vectors, it was easy. How do you keep pushing beyond? I'm going to record this process of elimination in this way. Okay, so I'm going to say this is my original set of coordinates I started with. Notice I'm already writing it as a matrix. It's very useful to write it like this. V1 to Vk, they are like this. I'm assuming my first pivot is non-zero. I've written U1 as V1 by A11, and then all the other Ui as Vi minus A11, Ai1 by A11 times V1. So I've eliminated like that. So after elimination, U has the same span of V, but then U has the simplified structure. So it's 1. The star basically represents anything. It could be 0 or non-zero. Okay, but I know the first position is 1 for sure. Then below that 1, I will have all zeros, and remaining things I don't know. Right? It could be anything. Okay, whenever I write star like that, interpret it as anything, 0, non-zero, 1, whatever. It could be any number that I don't know about. Okay, so this is my first step of elimination. I've recorded it like this. So when you work it out by hand, you have to record it like this. It's very useful. How to make the pivot position 1, 1 non-zero. So there was this question that I'm assuming A11 is not 0. What if A11 is 0? What do? You can exchange rows. Okay, there's no problem. You don't lose anything by exchanging rows, but you have to exchange only rows below you. Okay, so keep that in mind. You can't exchange rows above. For A11, it's okay, it's reasonable, but you always will exchange below. You will not exchange above. As you go forward, you'll see from 1, 1 there is only below, so you exchange from below. You can also exchange columns, but anytime you exchange columns, it's good to record it somewhere. Okay, so keep a record of it if you exchange columns, but you can exchange columns, and you can exchange columns to the right. Okay, so from right you can bring it here. I'll show you one example later on, but you'll see that you can also exchange columns. Now, if neither exchanging rows nor exchanging columns become possible, you actually will end up having an all zero row, right? So all zero rows are a bit boring, or maybe they'll be interesting, but that's also important. Okay, so keep that in mind. Okay. All right. So now comes the next step. Whatever we did for the first, we will try and repeat for the second, but then not disturbing the first in any way. Okay. So we'll focus only on row 2 to row k and column 2 to column k. Okay. So notice this red subsquare here. We won't consider the entire matrix. We'll only consider 2 to k. 2 to k in the columns, 2 to k in the row, and we'll think of 2, 2 as the pivot thing. Now we've gone to a smaller matrix. Okay, so it's sort of divide and conquer. Change the problem into a smaller problem and try and solve it. I've gone to a smaller thing here. Okay, think of the pivot position as 2, 2, and then keep proceeding. Okay, as long as I can make my pivot non-zero, either by exchanging rows below or columns to the right, I will divide by that pivot and then subtract all the below guys with respect to the pivot and make 0 here. I will get 1 here and 0 here. And then what will I do? I go to 3, 3 to k, right? So 3 to k. Smaller thing here. Again, if I can make that pivot non-zero, I'll make that as 1 and make everything below 0. So notice how it's going, how it's going, how it's going. When will I get stuck? When will I stop? If I cannot find any non-zero here, then I will stop, right? At that point also, you can push that 0 row below, bring any non-zero row above, and then column exchange. So you can keep doing as long as you can by some exchange make the pivot non-zero with below. Okay, you cannot go back above and redo anything that's above you. As long as below you can manipulate and keep doing it, you can keep on going till you get some non-zero pivot. Okay, finally when will you get when you have to really stop is if there is only zeros below you. Okay, everywhere to the right and below you, if there are only zeros, you will stop. Till then you will keep going. I'll show you some examples, then you will, I think, understand it a little bit better. But for now, this is an important fact. So while you're doing this, if at any point you got an all zero row, Okay, if one of your rows became all 0, then it turns out the vectors are linearly dependent, because what you're doing is at every stage, every row you get is a linear combination of V1 to Vk, right? So you're not doing anything other than linear combination of V1 to Vk repeatedly, further linearly combining. So finally, every row you get in this elimination process is a linear combination of V1 to Vk. Of course, there is that column permutation you have to do, but that column permutation doesn't change anything, it's just changing the ordering, right? So you have a linear combination of the V1 to Vk in every stage. Okay, so this elimination is very nice that way. You're only doing linear combination, but you're getting a nice structure in your linear combinations. There's 1-0 structure which helps you do things. So we'll talk about this a little bit later as we go along also. So at any point, if you got an all 0 row, you can determine that the V1 to Vk were linearly dependent. If otherwise, if you never got an all 0 row, you went all the way down to k with every row being non-zero, you could find a pivot throughout, then you have linearly independent set of vectors. So clearly, this is a very powerful method, right? Elimination is helping you determine whether a set of vectors are linearly dependent or linearly independent. Okay, so this is the first cue. As we see some examples, I'll come back and comment a little bit more on the structure. Maybe it's a little bit difficult for you to visualize. If you see a few examples, you'll visualize what's going on. Okay, so here are those examples. So let's take one or two interesting looking situations and then talk about it. Let's go to problem number 5. I'll urge you to do all of them. Work out these examples. Working out more and more examples is what's going to really help you. So I'm going to show one or two examples. I'll do question number 5. Okay. The question number 5 starts with, notice how I'm simply writing, in matrix form. This is very common. We always write in matrix form. Okay. It's easy to write. So these are basically 3 vectors. I have my V1 here, V2 here, V3 here. I just write it as a matrix form. Okay. My A11 is non-zero, so my pivot is already established. So I have to make everything below my pivot 0, right? That's my first step. So notice how I'm recording this. This is how I'll record it. I'll keep row 1. So since it's all matrix, it's very easy to write row 1. And then I'll make row 2 as row 2 minus 2 times row 1. I'll make row 3 as row 3 minus 3 times row 1. Okay, so this is a standard way to record eliminations. So the first row remains the same. Okay, or if you want to be very careful, you can write row 1 as row 1. Okay, and then row 2 is row 2 minus 2 times row 1. So this becomes 0, minus 1, minus 2, minus 3, right? And then row 3 is row 3 minus 3. So this becomes 0, minus 2, minus 4, minus 6. Do you get that? Is that okay? So now I have to look at my second pivot. Okay, I have to make it 1. So my first row is now unaltered, right? So I'm not going to touch row 1. So I'll make it. So if you want, we can draw that red box here. My red box is here now. I'm worried only about this guy. Okay, so I'll go to my pivot, second pivot. So my second pivot, row 2, is going to be row 2 by minus 1, right? So I'm dividing by minus 1 or multiplying by minus 1, both of them are same. So it becomes 1, 2, 3. Now what do I do for row 3? Row 3 is going to be row 3 plus, okay, so divide by minus 1, it's going to be minus, so my row 2 is still minus 1, minus 2, minus 3, just keep that in mind. So do it with only the previous one, R3 minus 2 times R2, right? So this minus 2 times this, it remains 2, this becomes 0, minus 2 times this becomes 0, minus 2 times this also becomes 0. I hope you see that. So you got a 0 row. You see that? So I got an all 0 row. And I can't proceed. I can't do a smaller box here. I can't go to the next level. I'm stuck. So this is where my elimination stops. So from here I can conclude V1, V2, V3 are linearly dependent. You see that? Because I got an all 0 row. Okay. So notice how up until the position where I get pivots, I'm going to get this upper triangular like structure with 1, 1 and 2 on top. All these guys could be non-zero, but once I stop getting a non-zero pivot, I will be only all zeros. Okay, so I hope you see this. This is a simple nice example. Maybe one more we will do with 4 of them. Okay, so it looks a complicated case. 0 0 1 1 minus 1 0 1 2. I hope I can write that down. Write that down as a matrix 0 0 1 1. I think that's right. Minus 1 0 1 2. I've just come up with a bunch of zeros. Maybe I may have to do some swaps here. We'll see that. 0 0 2 5 0 0 0 4. Oh, I have no clue what's going to happen to these guys. So I have these 4 rows. I mean, I personally prefer to swap rows first before I swap columns. It's just a matter of convenience, but because swapping columns I have to keep track a little bit if in future I want to find something out. But at this point I'm only determining linear dependence, independence, so it really doesn't matter what I do. But anyway, I'll swap columns. So I'm going to swap rows. I'll swap R1 and R2. So notice how I'm recording a row swap. So this just becomes minus 1. So I can also divide by, I can divide by just minus 1 to make it all very nice. So I'll get 1 0 minus 1 minus 2, and then remaining I'll just keep as it is. Okay, so this is my first step. So now I come to my second part. The first pivot is done, and below my first pivot all of them are already 0. Okay, so I don't have to do much. It seems easy enough. So now I come to my second smaller part. So here I notice that I have a 0 here. I'm stuck. I can't do any row exchange. If I do a row exchange also, I'll still be 0. So I need a column exchange here. So I can do maybe C2 C3, right? C2 C3, and luckily that's 1, so I don't need to bother too much about it. So keep track of these guys. So I have 1 0 0 0. C2 C3 column exchange, and then 0 0 0 0 minus 2 1 5 4. Nothing much changes after that. So here I have a pivot here, okay, and then and the next step I would do R3 is R3 minus 2 R2, right? So make everything below this 1 as 0. So notice how it's proceeding very systematically, if not very boringly, to get what you want. So R3 is R3 minus R2 R2, so you get 0 here, 0 here, 3 here, right? 5 minus 2 is 3, and then the last one remains the same. Okay, all right. So I've got 1 1 here, and then now I need to go to my next pivot. Here again I have this interesting looking situation where I got this guy. So again I will have to do a column exchange. So I'll exchange C3 and C4. Okay, watch out that C2 and C3 originally got exchanged. Now I'm exchanging C3 and C4 again. It's a little bit more tricky here. 1 0 0 0 minus 1 1 0 0. C3 and C4 got exchanged. We'll see later on how all this can be very systematically captured when you really want to use this for any particular case. At this point, I'm just trying to keep track of the modifications we are doing. So now again, I'll have to divide by not C3. I'll have to divide R3 by 3. Okay, so I'll do that. That doesn't change anything. I'll make 1 here. These are simplifications just to make sure you do things properly. And then the last one is R4 is R4 minus 4 R3, and this will give me 1 minus 1 minus 2 0 0 1 1 0 0 0 1 0 0 0 0 0. So notice how I have this wonderful looking structure. Let me just highlight the structure to you. Maybe I'll do that in blue. I got this upper triangular type structure here with all 1s on the diagonal. Okay, and then we have this zeros here, right? Zeros here, and then we have, in this case we have zeros here, but it could be anything. Okay, and then below everything we have 0, because that's when we can not proceed. So because of this, this becomes linearly dependent. So the V1, V2 are linearly dependent. We determine that they are linearly dependent. Okay, and that's how we proceed. Okay, so notice how elimination gives you a certain structure. You can try more general matrices. Just take 4 vectors of different type and see how you end up in a very reduced form for the overall matrix through elimination. Okay, so you should be very, very, very comfortable with elimination. It's a very important tool. You can do it in small cases like this, but in larger cases, it's better to use a computer program. Later on, I'll show you some computer programs with which you can do these things very, very easily. Okay. So, here is a reduced form after elimination. We saw a few cases, and you can go through this and establish that once you start with V1 to Vk and you eliminate, you will finally get a structure like this. Okay. So, you will get this upper triangular form just like I showed you, with ones on the main diagonal, zeros below it, and anything else to the right and above it. Okay. Above this all ones, and to the right of it you may get anything else, we do not know, that depends on the situation. But once you have stopped here, you can't find any more pivots. Below that entirely you will have zeros. Okay. So, this is how you will end up finally. Maybe R of the rows will be non-zero, remaining will be 0. In this case, what happens is span of V1 to Vk still remains the same as span of U1 tilde, U2, UR tilde. What is this tilde I am doing? You may have done some column exchanges, row exchanges do not matter, but you may have done some column exchanges. Whenever you did a column exchange, you have to record and go back and undo all the column exchanges to go from U to U tilde. Okay, it is just a permutation of the coordinates. So, that is just to compensate for whatever exchange you had to do. If you do that, you will see that span of V1 to Vk is exactly equal to span of U1 tilde to UR tilde. Okay, so that is an important fact. So, there is a reduced form you get after elimination, an upper triangular reduced form you get always after you finish all of the elimination process. Key point here is the U1 to UR, these vectors are linearly independent. Just think about why that happened, right? For two vectors, it was very easy to see. When you had a 1 and a 0 and these were non-zero, clearly you have to have linear independence here. But notice same thing happens here. If you have this ones, because these ones are on this diagonal form and everything below it is 0, you cannot make a linear combination of these guys go to 0, a non-trivial linear combination, because if there is a linear combination that is going to 0, all the coefficients because of this upper triangular structure have to be zeros, right. So, if you see a linear combination of these guys is going to 0, if you look at the first coordinate, clearly what scaling U1 has to be 0, right, because there is a 1 here, everything else is 0 here. How will you make the linear combination 0? Only if this coefficient is 0. Once that coefficient is 0, you come to this guy. To make this 0, second coefficient has to be 0. Likewise, you can proceed. So, this is this upper triangular structure which forces only the trivial combination to be 0. Now, you may say U tilde is a permuted version of U, but that is the same, right. It is just wherever you permute, after the permutation, you will have the same sort of upper triangular structure. You can argue the same way to get all 0 coefficients. So, this is very important. So, because U tilde are permuted versions, these are also linearly independent. So, you started with the V1 to Vk, span of V1 to Vk was a subspace, maybe you did not understand it better, understand it very well. Now, because of elimination, I am able to get a U1 tilde to UR tilde, which also gives you the same span, but they are linearly independent, number one, and they have this nice upper triangular structure to begin with. Okay. So, this is the nice thing about elimination. In fact, so this is the power of elimination, giving you this upper triangular form and a simple version of the basis. Immediately it allows you to decide on linear dependence, independence, right. We will push this further and do even more reduced basis, right. You have one basis to begin with, one spanning set to begin with. So, all these things will define precisely, understand how elimination is helping us to understand subspaces better, and that is the topic of the next few lectures. Thank you very much.